In this video, we're going to talk about Unit 4, Objective 3, Relative Extrema. Relative extrema, there are two different types. There are relative min or relative minimums, and there are relative maximums. Now, you've probably seen relative minimums and relative maximums before. If I draw just some random function over here that looks like that, each little peak or valley that we have here is either going to be a relative max or a relative min. So right here in blue, we have a couple of relative maximums, and then in red, we have a couple of relative minimums. Now, the reason they're called relative max and relative min is because they are higher than everything else or lower than everything else in its general area. So if we look at this first blue one here, everything in this little interval here to here, that blue dot is higher than all of that stuff. But if we look at the end of my graph, we know that we're increasing to infinity, so all of these points as we go farther and farther to the right are going to be higher than this first blue point over here. But in its general area, this blue point is higher than everything else. Same idea with this point over here, this red one. It's lower than everything else around it. It's not as low as this one, and it's not as low as what we have going to infinity. But in its general area, that red dot is a minimum. So that's why it's relative. It's not on the global scale. It's not the absolute minimum, but it's a relative minimum. So the calculus behind this is a relative minimum is when f prime of x changes from negative to positive. So we don't want to think about the words, or we want to think about the word slope, but we don't want to say the word slope. We want to keep it in terms of f prime. So if we think f prime changes from negative to positive, f prime being negative means we have a negative slope like we do here. Then our f prime is positive here, and that's going to give us a minimum. So just like when we were trying to find increasing and decreasing, because that's all we're doing here, we're just trying to find when f changes from a decreasing function to an increasing function. We want to start with f prime of x equals 0 and f prime of x is undefined. DNE just means does not exist. So same idea for a relative maximum. That's when f prime of x changes from positive to negative. And we want to start the process the same way. We want to think about when f prime of x equals 0 or when f prime of x is undefined. There's another way that we can prove relative max and min that we'll talk about in a second using the second derivative test, but I want to start out with just using the first derivative test, what we have here, using the first derivative to find out if my function changed from an increasing to a decreasing or a decreasing to an increasing function. So let's think about the function y equals 2x cubed plus 4x squared. And let's find all relative extrema. So find the relative maximums, find the relative minimums. So relative extreme values come from the first derivative. So again, we want to think, when is the first derivative 0? When is the first derivative undefined? So let's take the first derivative. We'll get 6x squared plus 8x. This will never be undefined. So it never does it not exist. So that's kind of a double negative saying it always exists. So we just need to think about when does that equal 0. So 0 equals 6x squared plus 8x. We can factor out a 2x, which will leave us with 3x plus 4. So f prime, or in this case y prime, equals 0 when x equals 0 and when x equals negative 4/3. So we can make our number line. I shouldn't call it f prime because our function's called y. So let's call it y prime. We have negative 4/3 and 0 on our number line. So if we take something that is smaller than negative 4/3, let's just say negative 5, and we plug it into y prime. So negative 5 times 2 is negative 10, so that's a negative number. Negative 5 times 3 is negative 15 plus 4, that's a negative number as well. A negative times a negative is a positive. Taking something between negative 4/3 and 0, we'll say 1. Negative 1, sorry. So negative 1 times 2 is a negative number. 3 times negative 1 is negative 3 plus 4 is a positive number. So we have a negative number times a positive number is a negative number. Take a number bigger than 0. Say take 1, you'll have 2 times 7 as a positive number. So we know our derivative goes from positive to negative to positive. So if we look in this first part here, my derivative changes from positive to negative. So if we think about derivative being the slope went from a positive to a negative slope, and right in the middle of it we had a spot where our derivative was 0. So we know we have a maximum when x is negative 4/3. And if we look at the other piece, let's not use yellow, let's go with red. Our derivative went from negative to positive, or our function went from decreasing to increasing, so we know we have a minimum value there at x equals 0. So we know where our relative extreme values happen. We know we're going to have a maximum when x equals negative 4/3, and we know we're going to have a minimum when x equals 0. But the question asks, find the relative extrema, not where do the relative extrema happen. So they want y values here. So we can say the max will be located at negative 4/3, comma 2.370. You can throw that in your calculator and get the y value. And our minimum is going to be when x is 0, plug that into our original function, and we get a 0 out. So we have the max and min at those 2 points. A lot of times AP will ask just where or what is the x value of the relative min or max, but this one actually wants us to find the relative max and min. So if we were to look at a graph of this function, it looks something like this. So you can clearly see that our function had a positive derivative here, a negative derivative here, and then back to a positive derivative here. So this value right here is going to be our maximum, that value is going to be our minimum. Notice in each place that the tangent line had a slope of 0, so our derivative was 0 in each of those cases. Now, let's talk about how we can answer that same problem but use the second derivative. So when you have a polynomial function, you can do what's called the second derivative test. So when we know where our critical points are, and that's something we should have defined earlier, and I apologize for that. Let's go back a slide, and let's define critical point. A critical point is when f prime of x is 0 or undefined. So we want to start with our critical points when we're thinking about maximums and minimums. So if we know where our critical points are, So you still have to take the first derivative, set it equal to 0, find when it's undefined. But once you get these x values that are critical points, you can use the second derivative to find out if they are maximums or minimums without using our number line. So how we would do that is we would take our second derivative. So our second derivative is going to be equal to 12x plus 8. If you were to take those critical values and plug them into our second derivative, you would get, if we plug 0 in, you get 8. If you plug negative 4/3 in, you're going to get negative 8. So what this tells us is the second derivative is our concavity. It tells us about concavity. So we know at y equals 0, the second derivative is positive, which means I'm concave up. So if I'm concave up and I have a critical point, which means my derivative is 0, right? So if my derivative is 0 and I'm concave up, I have to have a minimum value. If we look at negative 4/3, our second derivative is negative, so we're concave down. We know it's a critical point, so the slope of the tangent line is 0. So if the derivative is 0 and we are concave down, we have a maximum. So there's your second derivative test. Now it's only really useful if you have polynomials, something easy to take the second derivative of. Now there's one thing I want you guys to be careful of. So I want to look at one more problem. And let's say just y equals 4/3, or x cubed. And I want you to find all extreme values again, relative extreme values. So find all extrema. So we start with our critical points. So we take our derivative and we get y equals 12x squared. That's never undefined. So we set that equal to 0. And we have a critical point when x equals 0. So if we think about our number line, it should be y prime, but we'll keep it as f. If I take a negative number, say -1 squared is positive 1 times 12, positive. If we take positive 1 squared is 1 times 12 is positive. You'll notice that my derivative did not change. It went from positive to positive. That is going to give us what's called a saddle point. Saddle points are where concavity is going to change, but it's not a maximum or minimum. Now, if you want to try your second derivative test on this, your second derivative is going to be 24x. If we were to plug 0 into that, we get 0. Now, our second derivative, remember, tells us concavity. 0 is not positive, nor is it negative, so I have no concavity, so I don't have a maximum or a minimum. If we look at the graph, there is the graph of 4x cubed. So you'll see that right there at 0, 0, the slope of the tangent line is 0. But you'll also notice that I don't have a maximum or a minimum around it. My derivative went from a positive slope to a positive slope. So we don't have any max or min. So be careful when you have your derivative. Don't automatically think it's going to be a maximum or a minimum. It might be what's called a saddle point. So that'll do it for this video. We'll see you in the next one.